Good afternoon, Copenhagen. Good evening, Copenhagen and Christiana. It's really wonderful to be here. And you probably don't know this, but actually, Copenhagen has a role in my scientific beginnings. I was a graduate student here at the Niels Bohr Institute when I first started my PhD. And I have wonderful memories from the year that I spent here. So, without further ado, I would like to tell you about this crazy image that we took of a black hole, of all things. And we published it back in April of this year. And you probably have seen it. It looks something like this half-eaten donut. Or a coffee stain. Whatever. So I would like to tell you what that image tells us. I would like to tell you how we got there. So let me begin by orienting you in the sky, in the night sky, because these are constellations you can see from up here in Copenhagen on a clear night. So let's begin by finding the Virgo cluster here, the Virgin. And right in between the arms of the Virgin here, there is a cluster of galaxies, much like the Milky Way and even bigger galaxies, called, not surprisingly, the Virgo cluster. And in that Virgo cluster, this is the cluster of galaxies. You can see individual members of this cluster. But there is one called the M87 galaxy. It's in the Messier catalog number 87. It's not the most massive member of that cluster, but it's the brightest member of that cluster. So the galaxy shines. And we've known about this for a very long time. It's a galaxy we've been studying for more than 100 years. And what is special about it is that now going from this image of the entire cluster to a Hubble Space Telescope image and zooming further in, it has this elongated structure coming out from the very center of the galaxy that we call a jet. A jet because it's a lot of radiation, light coming out of the center of the galaxy. And it is very energetic, so we know something is up, right? The jet is comparable to the size of the galaxy, so something very powerful must be providing energy to it. So for years, we thought there must be a black hole at the center of this galaxy that gets gas from its surroundings, the stars that happen to come too close, basically it swallows them, and there must be this black hole that is growing as a result of eating this gas. And in some black holes, M87 is not the only example, we also see this jet that forms during this accretion process, this eating of gas. So that was the first clue that we're dealing with a black hole there. Why did we choose this black hole? Why did we have to go to M87? Actually, we chose two black holes. One is this one, which I'm going to talk the majority of this evening on, the M87's black hole. And the other one is actually our own black hole, Sagittarius A star, towards the constellation Sagittarius. It's the center of our own galaxy. And there is also a very massive black hole there. Not quite as big as M87's in mass, but because it's closer, it also looks large in the sky. So if you want to take a picture of something, you want it to be, and you want to see details of what is going on. For example, is it really a black hole? Is there a hole at the center? Things like that. You want to be able to capture as much detail as possible, so you want to look at something that looks as big as possible in the sky. Black holes look big for two reasons. One, if they are close to us, we don't have too much control over that, but there's a selection in our neighborhood. And two, if they are massive. The more massive they are, the bigger that image is going to be. So we chose our top two targets, Sagittarius A star and M87, and observed them. Okay? So when I say it's big in the sky, it's relative. We are talking about astronomy after all. So let me start by orienting you about what kind of a telescope we had to design in order to really get that image. How big is the moon? It's half a degree in the sky, so the size of your thumb or your index finger as you hold it at an arm's length, okay? You can cover the moon with it. So as an angle, we call it half a degree in the sky. Okay, we start there. We divide that into 60, because we're working with, just like there are 60 minutes in an hour. So we make 60 arc minutes, 60th of a degree out of that. Okay, I'm going to keep going. We're going to make 60 arc seconds out of that. And then arc seconds, we're going to divide into 1,000. We're going to make milli-arc seconds. By now, we're down factor of quite a bit from a degree. And then we're going to divide that by another 1,000, and we're going to make 1,000 micro-arc seconds, millionth of a degree. Okay? So the black hole that we are aiming at is 40 of these units in the sky, 100 millionth of a degree. So if this sounds crazy, it's because it is crazy. How could you possibly take a picture of something that is so tiny in the sky? And one way to think about it, because we really don't think about millionths of degrees, if we put a donut on the moon and we said, okay, take out your camera, I want a picture of that, that's how it would be. Okay? It would be the equivalent of taking the picture of a donut at the distance of the moon. But that didn't stop us. It's okay that it's crazy. We basically said, we can do this. So we thought about what telescopes we can use. There are two important things when you're choosing a telescope. One is it has to be the right wavelength, and I will come back to that. It turns out to be millimeter wavelength of light, so not the visible, not infrared, not long wave radio, but something in between, which has a wavelength of 1 millimeter, turns out to be the right place to do this experiment. The other thing you want, if you want to resolve detail, is you want your telescope to be as big as possible. So this would be what the backyard telescope would look like, a very high-quality backyard telescope. That certainly won't do the job. Okay, how about the biggest telescopes we're building as one continuous object? So even though the lenses are separate, they are still physically attached to one another. So this is one of the 30-meter class telescopes that we're actively working on in the world right now. This is the giant Magellan telescope. It's not even operational. That won't do it. That is just that it doesn't have the resolving power to take the image of a black hole that is so far away and so small in the sky. It turns out what you need at the 1 millimeter wavelength is a telescope the size of the Earth. Okay? If it's just as big as the diameter of the Earth, we're in great shape. So we went to lots of funding agencies, both in the US and in Europe, and we said, can we get a little bit of money to build a dish the size of the Earth? And we failed. So we went to the next best thing, which is a technique called interferometry. In interferometry, what you do is you pretend you have a big telescope. You put one telescope on one part of the globe, another telescope on another part of the globe. You look at a distant object, like our black hole, at the same time, and you faithfully record your data. When I say faithfully record your data, every wavelength of the light that's reaching you from your black hole, the surrounding environment of the black hole, has to be recorded, every up and down, and time tagged. Okay? So we record them with the precision of a hydrogen maser clock on specially made hard drives that are able to record data fast. And not just fast, but these telescopes are at high altitude. Some of them are thousands of meters high. So it also has to be basically space-qualified hard drives. Okay? So let's say this is one telescope receiving the signal from a black hole. This is another telescope. And then we physically take these hard drives, join them in a correlator, match up the signals. And it doesn't have the collecting power of a telescope the size of the globe, but it has the resolving power of a telescope the size of the globe. So this is what we set out to do. The proof of principle observations were done in 2006 to show that this method actually worked for the purposes that we wanted, using 3 telescopes, one in Arizona, one in Hawaii, and one in California. And after that initial set of observations, we set out to equip what became the Event Horizon Telescope Array. So in 2018, when we first took the global data, there were 8 telescopes on this array. We keep working on it. As of now, there are 10 telescopes on this array. So I'll take you on a little tour. This is the Spanish Alps. This is the South Pole. Yes, we have a telescope in the South Pole. There are 2 in South America, ALMA and APEX in the Atacama Desert, Large Magellan Telescope in Mexico, submillimeter telescope, and now a new one, Keck, in Arizona, and 2, JCMT and SMA in Hawaii. This way, we have north, south, east, west coverage, and as of last year, we also have the Greenland telescope on this array, so that our now longest baselines, even though they can't operate at the same time, we can go as far as practically the North Pole and as south as the South Pole. So we have these 10 telescopes spanning the globe, and we do these observations where pairs of telescopes look at a distant object at the same time, record data the way I described it, and then we try to combine the signal and make an image. So while we were outfitting these telescopes, a few other things were happening at the same time. We were also accumulating people. This is from the inaugural meeting in Tucson, Arizona in 2012. And this is from a recent collaboration meeting in Nijmegen in the Netherlands, November of last year. And you can see, this is not even half the collaboration in this picture. We've grown to more than 200 people. We cover basically every time zone available, which makes teleconferencing a pain in the... There are lots of times I'm either on a 5 a.m. telecon or a midnight telecon just because it works someplace else. But apart from these growing pains, we really enjoyed growing the hardware, the capabilities of the telescopes, and growing the collaboration. So just because I am from Arizona and I've come all this way, I want to bring you a few more pictures from the telescopes that I'm intimately familiar with. This is the submillimeter telescope on Mount Graham in Arizona. Arizona is also, especially southern Arizona, is a desert, and every peak on that desert is basically laced with telescopes. And this is one of them that operates in the millimeter wavelengths. This is the new 12-meter telescope on Kitt Peak, which has joined the array. And this is a picture of the South Pole telescope. There are many people in the collaboration whose job it's been to provide the right type of hardware, the right type of recorder, the right type of instrument for these telescopes. And this is the one that was done at the University of Arizona by my colleague Dan Maroney. It's him here. This is about 5 years ago, when he still looked young, before the many trips to the South Pole. You should see him now. This is his graduate student, Junhan Kim. And this is the receiver that they built and gold-plated. Gold is a very good conductor, so it can keep a uniform cold temperature. That's why we cover our instruments in gold. And this is the cover. So they took this down to the South Pole. This is their pictures. This is what it looks like. They actually have to take a military plane, and they have to travel as cargo to get there. So this is the interior with the people and all the equipment they're taking down. But I don't think that stops them from having fun. There is an annual around the globe race that Junhan participated in, as you can see, proud of his penguin costume and his race number. Okay, so just a few more pictures. The reason I want to show this to you is now this receiver is down in the South Pole, already mounted onto the telescope there, the sub-millimeter telescope there. And just briefly, I want to show you the backends also. Backends meaning all the recorders and the electronics that are needed, because I said we have to faithfully record the data. It's a lot of data. These are all racks full of drivers and converters and hard drives. So this is, they left the instrument. Actually, I'm just going to stop the, oh, I can't stop it. So, okay, you'll have to listen to it. So they take it down during the South Pole summer, which is our winter, and they mount it, they leave the instruments there, and then the winter rovers actually do the observations for us. The reason is that now we're talking about 8 different locations across the globe, and we want to aim for good weather in all these 8 different locations. Okay, that's also crazy, but it turns out that end of March, beginning of April period happens to be the lowest moisture months in most of our sites. So obviously, it's not reliable. We still have to wait for good weather from a day-to-day point of view. But when mounting global observations, we aim for this April timeframe. So after all of this was done, the winter rovers in South Pole, our colleagues in all different sites, the first campaign was in April of 2017. And this is what it looked like. Some happy faces. You can see blue skies, sunshine. We had amazing weather. It was better than we could hope for. So we went day after day, night. Actually, the telescopes get warped. Some of the telescopes get warped during daytime, so we still had to do nighttime observations, even though we weren't observing in the visible. But we had many nights of great data. So what we did was make a makeshift control center. I'm right here, more screens than people, basically trying to get information from all different places. Are you ready? Are you technically ready? Is everything working? Is your weather good? Is the moisture in the atmosphere below our threshold, etc.? And we actually had a great time. April 5 to the 11th was the span of observations. This is now the large millimeter telescope in Mexico looking towards the center of our own galaxy, because we interspaced the observations of M87 with Sagittarius star. This is the disk of the Milky Way, as you can see. So at that point, we were done with the observations. We didn't know what we had. We actually had to wait a long time to find out what we had, whether our experiments succeeded, and what the scientific results were. The reason is that, as I said, we physically have to combine the data from these different telescopes. And we have 2 centers where we can do this. Take all of these EHT telescopes and take the hard drives and send it to 2 places. One is the Haystack Observatory at MIT, and the other is the Max Planck Institute in Bonn, close to here. So those 2 places combined all the data that was worth 5 petabytes. And once they combined it, we then launched the various data analysis centers, also using the Google Cloud in North America, transferred 5 terabytes. So basically, if I now give you a graphic of from the moment we collected the data to the end, what happened, here are the steps that we went through. We had 5 petabytes of data, as I mentioned. It turns out that if you just weigh them, they are more than half a ton, okay, just to keep this data recorded. So there is no internet speed that allows you to send it. So instead, what you do is you put them in crates. You literally put them on FedEx trucks, including from the South Pole. You wait for the summer, and then they arrive in these correlation centers. Luckily, nothing happened to our data. We had one close call. One set of disks were swapped with fabric swatches, of all things. That ended up in Bonn, and people freaked out for a little while, but then the mistake was corrected, so that was all good. So, from this, the 2 correlation centers, as I said, literally match up the wavelengths coming from different telescopes. That's called the correlation step. Then afterwards, we fit the waveforms that we find. That's called fringe fitting. So at each one of these steps, the data volume gets compressed by a pretty serious factor, by a factor of 1,000 in correlation, 10,000 in fringe finding. At that point, we have all the information that we need for an image. So we run our imaging algorithms and actually find the shape and the content of the image that describes it best. And finally, we had the announcement in April of 2017, after about a 2-year period where we did all of this, analyzed it, wrote our publications as the collaboration, and had a press event. So, thank you. It was indeed a big excitement. It was a big relief that we worked, that we were able to share it with the public. And we were truly humbled by the attention that we got. This is the, if it works, the following day, the front pages of newspapers around the world. And obviously, this was absolutely great because we love black holes. We love that you love black holes. And this was really the best reward for many sleepless nights. But I have to say my favorite was not the newspapers. If there are press members here, I apologize. My favorite was the memes. There were so many memes. And if I had to choose one, this has got to be it. Homer eating a donut. And we fully accept responsibility for this meme because we said it's the size of a donut on the moon so many times leading up to this experiment that we absolutely loved it. So let's go back to the image and now seriously try to understand, why does it have the shape that it does? Why does it look like a donut? Why does it look like a donut that's brighter on one side than on the other, right? The frosting is kind of missing on one side of the donut. So in order to do that, and I know you've had a drink or two, but I really need to take you on a mini tour of Einstein's theory of general relativity. Right? What's better for science and cocktails than a little general relativity? And I want to explain to you how gravity works in that theory and why it produces black holes in that theory. So what Einstein says is that space and time is just a fabric that is able to respond to the presence of masses. So what that means is that if we look at the space and time literally as a fabric, and for your convenience, I've drawn a grid on it, and what I'm going to do is shoot straight lines of rays on this fabric. If there is nothing in that space-time, it is flat, just like a fabric would lay flat. And the light, the different rays of light, would simply follow straight lines on this fabric. So here we are. We're looking at light rays traveling in straight lines like they've been told to do. But what happens when we put not just a mass, but a mass that is strong enough to bend the fabric to trap this light? So what will happen is that some of the rays coming too close to this, what is now a black hole, with an infinite little hole at the center of this fabric, is going to trap some of the rays. The others, as you will see, will get bent around a little bit and deflected, and others that happen to be just too far away from the black hole won't really feel its presence. So, as a function of the distance from the black hole, either they will get swollen, or they will get swallowed, or they will get deflected, or they won't even feel the presence of the black hole, okay? So this is what's happening here. Now, this is basically it. The reason a black hole forms in Einstein's theory of gravity, which we call general relativity, is that masses bend the fabric of space-time. There is a class of things that we end up calling black holes that bend space-time so much that they trap light in this well. Okay? So no light that ends up at the center of this object can come back out. So the center has to look dark. If there is a source of light around the black hole, some of it will be able to, that is far away, sufficiently far away from the black hole, will be able to escape and come to us, observers. Some of it will get deflected, and some of it will get swallowed. So that is the basis of the image that we are seeing. But obviously, we don't just do simulations of this type. What we are trying to understand is, really, in a black hole environment, how does the gas shine? Because the gas is coming from far away, from stars that passed a little too close and felt the gravity of the black hole. There is a flow of gas that formed around it, and it's slowly making its way down to the center. En route, it heats up, and it gives out light. So we really need to understand how that light forms and gets to us. In Arizona, about a decade ago now, maybe a little less, we started using a special platform called GPUs in order to do these simulations on very large scales and with as much physics as possible in what we are simulating. So you're familiar with CPUs. Most computers run on CPUs. But actually, GPUs, the graphics processor units, are pretty common too. Your phones have one. They have the ability to render parallel paths of light on your screen. That's the graphics card, basically, on your computer. So all we had to do was hack it, and instead of solving for normal straight paths of light, we solved Einstein's field equations on the GPUs. Okay? So it might sound weird, but it was actually a very logical application. So instead of showing you computer simulations, what I want to show you is my colleague C.K. Chan at the University of Arizona telling you basically how fast and how massive simulations we can run on this by putting, this is on his laptop now, this is a single GPU, and he's controlling with a device called the leap motion. And he's controlling an entire simulation, which means running it in real time, solving Einstein's equations for 1 million particles of light at the same time, throwing it towards a black hole. And you can see the ones that are trapped here in the space-time, leaving this classic hole in the image. So what we're saying is, as long as there is a source of light in the vicinity of the black hole, some of it will get to us, some of it will not. It will be absorbed at the center, and it will leave this characteristic hole, the blackness, at the center of the image. We've done this, as I said, on larger scales. We have run simulations where we followed the the gas around the black hole as it swirls around and heats up and develops all sorts of properties like magnetic field and many different things. So these were now run on specialized supercomputers, one that we built at my home institution with many, many, many GPUs, so that we could look at the black hole environment and look at the different types of images that we get, that we might expect as a result of this experiment. I will take this opportunity to do one more thing that I promised at the beginning of my presentation. I said you have to pick the right black hole in the sky, as big as possible. And I said you have to pick the right wavelength of light in order to do it. Now I want to come back to that. What do I mean by the right wavelength of light? Why can't we look at any light that we choose? Well, we want a wavelength of light that is emitted in the vicinity of the black hole, so something as high energy as possible. But at the same time, we don't want so much light coming from the gas that the torus itself is opaque. Otherwise, it's going to block our view to the center of the black hole, where we are hoping to see this shadow, this horizon, this blackness at the center. Okay? So this is, again, the result of a large computer simulation where we have thrown in the gas, thrown in all the general relativistic equations, and we asked ourselves, as we crank up the frequency of observation or crank down the wavelength, what do we see? Okay? So we are now at a long wavelength, like a centimeter, and what you see is that even though there is a black hole at the center, there is a little jet associated with it. The torus around it produces so much light that it's opaque. But look what happens when I'm going to crank up the frequency now. I'm just changing the observational frequency. And at this point, when we hit 1 millimeter, what we see is that the ring around it remains, but the center becomes transparent. So we are able to see through this whole flow of gas down to the horizon of the black hole, but there is still enough light to make a contrast and give us the image that we are hoping to get. The first part was zooming in at the right frequency, and this part actually now runs the simulation forward in time. And what this shows is that black hole environments are dynamic. The gas is swirling around, so we actually expect a little bit of change in the image as we look at it, as we observe it with our telescopes. So we've done, as the worldwide collaboration, many, many of these simulations. We've put in the physics that we know. We've put in the physics we can't resolve at this point with our computers and with our knowledge of the microphysics that happens in the vicinity of a black hole. We wanted to be ready for all possibilities. What if the mass of the black hole is a little different than what we thought? What if the gas isn't as transparent as what we thought? What if it's a little bit hotter or colder? So we've run, with the worldwide team, many thousands of these simulations, and this is just a collection that I've put up here for you to see. And what we see is that almost always the hole is there. Maybe the donut is a little bit fatter or a little bit thinner. Maybe it's a little bit brighter on one side, a little bit less bright in some other cases. Maybe there is more of a swirly structure, maybe there isn't. But the hole is always there. It is a characteristic of Einstein's theory of gravity. It is a characteristic of a black hole, and that is what should define what a black hole is. When we say we take an image, the primary thing we're looking for is that absence of light at the center. Now, from that to saying, was Einstein right, is actually a big step. Because there might be certain things about the theory that are right, for example, the existence of a horizon, but there might be certain things about the theory that are quantitatively not right. And there is a well-kept secret in the astrophysics community. It is that even though we say black holes are a prediction of Einstein's gravity. We fail to mention that Einstein hated the concept of black holes. He refused them his entire life. He never worked on black holes. He thought it was a failure of his theory, that it predicted the singularity in space-time. That usually signals the breakdown of a theory, and that's how he took it. Other people worked on it. Other people worked on showing the indirectly inferring the presence of black holes. And then other groups of people worked on saying, okay, within this theory, what should black holes look like? Is it sufficient to say that there is a darkness at the center? Or do we actually expect particular characteristics of that light ring and the darkness? So I just put up here a series of papers that I was intimately involved in that basically took the theory and turned it into something that we can test by these images of black holes, the first one of which you've already seen, and others that we're working on. So I'm going to tell you about two of these. One is, okay, now I have an image. Can I tell what the mass of the black hole producing that image is? This was a paper that we wrote in 2012. And the second one is, okay, you say you have an image. Is the size and shape right? Okay, so let's look at these in the last part of my talk. The first one is actually not a hard concept at all. There are some additional calculations involved that I'm not getting into the details of, but the idea is pretty simple. We say, okay, we have a bright ring here. It's brighter on one side because that's the side the gas is coming towards us. So through an effect called the Doppler shift, just like hearing the pitch of an ambulance higher and a bit louder as an ambulance approaches us, and lower and less loud as it recedes away from us. The same thing happens with light. As light is swirling towards us, it looks brighter on one side. It looks less bright in the side where the gas is swirling away from us. Okay, so we have those basics down. Now we can basically fit a size to this and say, okay, I'm going to go to the brightest part of this ring, and I know from my theory how it should scale with the size of the black hole. It turns out to be basically a linear scaling, meaning the bigger the black hole, the bigger the ring that it produces. And we measured from this image that it is 42 micro-arc seconds. As I said in the beginning, we were aiming for about 40. We wanted to be able to resolve something that is 40 micro-arc seconds across. The image turned out to be 42. That implies a black hole mass of 6.5 billion solar masses. Okay, 6.5 billion times the mass of our sun in a very small region. Is this right? Do we know anything about it? So can we say we're testing the theory or not testing the theory? Well, actually, it turns out we can, because we've done observations of stars that are circling around this black hole. Not individual stars like we can do for the center of our own galaxy, where we can literally follow tracks of stars, but as a whole. So the dynamics of the stars around M87's black hole. We've known for a while that pointed to a mass that keeps these stars in place and orbiting around them. And that turned out to be 6.5 billion solar masses. Okay? So it's not as precise as we would like to make for the next experiment with our galactic center black hole, but definitely the 42 micro-arc seconds implying a mass in a very different way than the orbits of stars around it. This is actually an animation of actual observations. It implies 6.5 billion solar masses. Okay. The next thing that we did is ask, is it the right shape? Okay? So we said we're basically expecting a circle. That's because in general relativity, no matter what you do, as long as you keep the theory the way it is, the shape has to be a circle, okay? But if I now say the theory is not complete, maybe we're missing something that happens at the quantum scale, or maybe there are other terms that Einstein didn't write down, then we can actually change the shape quite drastically. Okay? So a deviation from the theory manifests itself as a deviation from circularity in this image shape. Okay? So we did that experiment with the image that we already have. And what we can say today is that we already know that there is no deviation from a circle for this image that is larger than 10%. We're hoping to do better. We're hoping to get this limit down even further with future observations. But even now we say, yeah, it looks like a circle, and the uncertainty on that statement is of the 10% of the circular radius. Okay, so this is what we were able to do with M87. What is next? Well, as I mentioned already, Sagittarius A star is next. That is a very special black hole for our galactic dwellers. It's the Milky Way's black hole. So I want to take you on a little journey towards that as well, because we look towards the constellation Sagittarius through the disk of the galaxy, and we have to go quite a bit of ways. It's 26,000 light years away from us. M87 was 55 million light years away. So we're coming closer home, for sure. And the beautiful thing about our galactic center black hole is that, as I said, through large telescopes and a technique called adaptive optics, we've been able to resolve individual stars and follow them for about 20 years, making a time-lapse movie of these motions around the black hole. So that gives us the precise location where we expect it, and it gives us a precise number for the mass that we expect. So whatever we did for M87, we're also going to do even better for Sagittarius A star, which is what we're working on now. Next up, I said we needed a telescope the size of the Earth. Well, why stop there, right? Why stop with wherever we have landmass on Earth instead of putting also telescopes in space and being able to get many more pairs of telescopes looking at our object? Right now, we're limited in the amount of information that we can get by these 10 telescopes and the baselines that they form between them. But if we put telescopes in space, we can do one of two things. One is if we put them in an orbit swirling around the Earth, then it will give us far more information, just many different looks on our source than what we can achieve on Earth. It's like going to the doctor and getting an MRI or a CAT scan, a CT scan, and I don't know who has the experience of this. You basically go into a tunnel and the machine rotates around you, taking a look at you from 360, and then you synthesize all the signals into one image, one 3D image. The technique of interferometry is mathematically identical to that. So basically what we are saying is as the Earth rotates, instead of just looking at it from these discrete points of view, we also want to look at it with telescopes that literally swirl around the Earth and give us all kinds of views. The second thing it will do is we will no longer be limited to separations that are the size of the globe. Now we can maybe go a third of the way to the moon and get even finer structure, finer detail in the images that we're looking at. So a group of us within the Event Horizon Telescope collaboration are also working on, okay, what does it take to put millimeter dishes in space? What does it take to record the data there and then get it down to the Earth? Can we do it in a reasonable amount of time? Can we do it with reasonable computer power? So while we're working on the Sagittarius A star data, while we're working on developing our theories, we're also working on making the EHT from space doable. So I just want to leave you with, I already showed you the collaboration picture. We are more than 200 people who have put sweat into this project. This is my team at the University of Arizona, undergraduates and graduate students. And I've been very lucky to work with all of these people to make this possible. So with that, I will leave up the image and take questions. Thank you.